Having taken a short detour into understanding complex numbers, in particular the complex d-th roots of unity, we are now ready to apply our understanding back in the context of polynomial evaluation. And recall that polynomial evaluation requires us to pick some number of points at which the polynomial must be evaluated. And we have the freedom to pick appropriate set of points. So, in our context, we will be choosing the d-th complex roots of unity, and we will be evaluating the polynomial at these d-th roots of unity. So, recall that the polynomial a of x can be represented as a e of x squared plus x times a o of x squared. Now, a e comprises the even numbered terms and a o comprises the odd numbered terms. Now, the problem of evaluating a of x reduces to evaluating these two polynomials, each of degree at most d by 2. These are the polynomials a e and a o, and we need to evaluate these points at the squares of the points at which a needs to be evaluated. So, a needs to be evaluated at 1, omega, omega squared, and so on up to omega raised to the d minus 1. a e and a o need to be evaluated at the squares. However, these squares do not lead to d completely different values. They lead to the d by 2 complex d by 2th roots of unity. So, if we wanted to evaluate a of x at the 16th roots of unity, a e and a o are going to be the 8th evaluated at the 8th roots of unity, and we will not have 16 of them, we will only have 8 of them. So, let us look carefully into how this works. We want to evaluate a at the d roots of unity. So, that is starting from omega raised to the 0, omega raised to the 1, and so on up to omega raised to the d minus 1. Now, we are going to split it into the first half and the second half. So, we let k run from 0 to d by 2 minus 1. So, the first part we will be focusing on evaluating a at omega 0 up to omega d by 2 minus 1, and then subsequently in this second part we will be focusing on evaluating a from omega raised to the d by 2, omega raised to the d by 2 plus 1, and so on up to omega raised to the d minus 1. So, putting these two together, we will be evaluating a at all the d roots of unity, d-th roots of unity. Now, let us focus on a omega k. We know that a omega k can be written as a e omega square omega k squared, which is nothing but omega 2 k, plus omega k times a o omega k squared, which again can be written as omega 2 k. So, now recursively we would have solved and obtained the answer to a e here and the a o here. So, a omega k can be computed. Now, a omega k omega raised to the k plus d by 2 requires a little bit more work, but essentially we will see that this also can be easily computed. So, let us look at that. It can be written as a e of omega raised to the 2 k plus d. Basically, this is omega raised to the k plus d by 2 the whole squared. but when we square that, we will get omega raised to the 2k plus d plus omega k plus d by 2 times AO in time of omega k plus d by 2 the whole squared, but when we square it, we will get omega raised to the 2k plus d. Now, this term omega raised to the k plus d by 2 by virtue of property, the plus minus paired property, means that this is nothing but negative omega to the k. And omega raised to the 2k plus d is nothing but omega raised to the 2k. So, so now that we know how to evaluate each one of evaluate A at each one of these complex d-th roots of unity, we will put them together and design our fast Fourier transform algorithm. And here is the pseudocode for this algorithm. Just to recall, the input is going to be the coefficient representation of a polynomial A of x of degree at most d minus 1, and here d is a power of 2, and omega is is a complex d-th root of unity. It will typically be the principal complex d-th root of unity. The output is going to be the evaluation of A at A of omega to the 0, A of omega to the 1, and so on up to A of omega raised to the d minus 1. So, the polynomial must be evaluated at these d complex d-th roots of unity. Well, if omega is equal to 1, we simply in O of 1 time evaluate A of 1 and we return it. So, that is of course, the base case for our recursion, and that is quite easy to see how it works. And now, if on the other hand we are dealing with a higher d value, say, but recall that d must be a power of 2, then we can represent A of x in the form AE of x squared plus x times AO of x squared. And in order to recurse, we first evaluate, we recursively evaluate the AE and AO at the d by 2th roots of unity, and this can be achieved simply by calls, recursive calls to FFT. So, here we call FFT and we pass on the coefficient representation of AE and specify that we need to have evaluated it at the d by 2th complex d by 2 complex d by 2th roots of unity, and once we once we've evaluated it at AE, which will be basically the at the even powers of omega. So, we will then have all of the required evaluations of AE. Similarly, we recursively call a FFT on AO again at omega squared. So, this specifies that we are again evaluating AO at the d by 2 complex d by 2th roots of unity. So, the line numbers 3 and 4 provide us with all the evaluations needed for AE and AO, but our goal is to evaluate A, and towards that we compute each of the evaluations inside of a for loop going from 0 to d minus 1, and this is quite straightforward. So, A of let us say omega raised to the A of omega raised to the j is going to be AE of omega raised to the j the whole squared, but that is going to be omega raised to the 2j plus omega j times AO of omega j raised to the whole raised to the 2, which is nothing but omega raised to the 2j. And since we know all these terms, we can in the right hand side the evaluation A can be evaluated at omega j. And once we perform all of these evaluations, we return them, because now what we have is the polynomial A evaluated at omega to the 0, omega to the 1 and so on up to omega raised to the d minus 1. Now that we know how the polynomial A can be evaluated, let us move towards polynomial interpolation, which is another step in the polynomial multiplications algorithm. And for that, let us focus first on what we even mean by evaluation. We have a polynomial A represented by its coefficient vector, and in order to evaluate this polynomial at the complex d-th roots of unity, we have to essentially perform a matrix times this vector. And what is this matrix? Well, each row is going to be starting at 1, and let us say we want to evaluate the polynomial at omega raised to the 1, then the row corresponding to that will be 1, omega to the 1, omega to the 1 squared, omega to the 1 cubed, and so on up to omega to the 1 whole raised to the d minus 1. And so we have already seen that performing this matrix times this vector will evaluate all this polynomial at each of these d-th roots of unity, and the evaluations will be obtained in this column vector. And whenever and this matrix is, we represent that, we denote that by m, and notice that the key parameter here is the appropriate principal d-th root of unity that immediately defines this the sequence of elements that we will put in each of these rows. So we can represent this m in parametrically as m subscript d omega, where omega is the appropriate principal d-th root of unity, and here of course d represents the dimension of this matrix. As we have also observed in the past, this matrix is a van der Monde matrix, because if you take any of the rows in this matrix, the terms are going to be in geometric progression. And the fact that M is a van der Monde matrix implies that M is invertible. So this means that if you have a matrix times a vector m times a, and m is and if it leads to y, then m is if invertible. So a can be obtained by multiplying the matrix M inverse times the vector y. So here is a quick exercise that will help us understand how to perform polynomial interpolation. Consider this matrix M. we have already seen that matrix M is a van der Waals matrix and it is invertible. Now, your exercise will require you to show that M is the columns of M are orthogonal. And if the and using this notion of orthogonality of the columns, you are now required to show the following equality. Now, for this we will need a little bit of notation. The matrix M is denoted in more detail in the following way: M subscript D omega. So, this denotes that we are talking about a D cross D matrix in which the elements are based on omega. So, this MD omega refers precisely to this matrix represented here. Now, we want to show that the inverse of this matrix, essentially the inverse of this matrix is nothing but 1 by d md of omega minus 1. Now, what is this md omega minus 1? It is essentially this matrix, but with each of the omegas replaced by omega raised to the minus 1. So, we want to show that taking the inverse of this matrix, which is what is required for us to perform polynomial interpolation, is essentially 1 by d times the matrix M, except instead of omegas, we will use omega to the minus 1. Now, if we are able to show this, we get a very nice consequence. Let us see what that is. We can modify the FFT algorithm that we've already seen and perform interpolation, which is we originally used FFT for polynomial evaluation. In this context, we are actually going to perform interpolation using the same FFT algorithm in O of d log d time, which is the more efficient time complexity. We already know that the polynomial can be evaluated using direct application of the fast Fourier transform algorithm given the coefficient representation of the polynomial, followed by the omega, which is the principal dth root of unity. Now, to interpolate the polynomial, meaning to interpolate and arrive at the coefficient representation of the polynomial given the point value representation, we again have to apply the fast Fourier transform algorithm. The inputs to this will be the point value representation of the polynomial, and instead of using the principal dth root of unity omega, we will have to start with omega to the minus 1. And after we perform this FFT, we will have to divide the end result by d, and this will give us the coefficient representation of this polynomial, thanks to the exercise that you have proved here. So, let us now recap what we have seen so far. We have viewed objects like Boolean functions, polynomials, periodic functions as vectors, and we have described the notion of the Fourier spectrum, which is essentially viewing these vectors in some alternative basis. typically the Fourier basis. And we have defined the notion of the spectrum as essentially the vector representation in the Fourier basis, and the Fourier transform is essentially the changing of the basis from the standard basis to the Fourier basis. So, if you have a vector in representation of, say, a Boolean function of or of a polynomial in the standard basis, we can change that into its representation in the Fourier basis, and that would be called the Fourier transform of that vector. And we found that this has lots of nice applications. We have looked at how a lot of the signals in the real world context are actually sparse. And this is also very true in the context of big data, where data gets generated in large quantities, and so representing the data in its direct form might be very complex. However, in a lot of real world big data applications, we might encounter the notion of sparsity, where if we were to transform the data appropriately, we would be able to represent the data in a much more compact form without really losing much information. And so, this transformation may play a very crucial role in big data applications. We have also seen that as transformations of this form provide us with significant benefit in the context of polynomial multiplication. So, when we want to multiply two polynomials, we have seen that we can actually perform them after transforming the polynomials into the appropriate Fourier basis, or what we call in particular the Lagrange basis, with at suitably chosen complex points. We were able to then perform polynomial multiplication in O of d log d time, and this was a very nice divide and conquer strategy that helped us achieve this O of d log d time. So, now we will end this sequence of lectures by talking about signal processing a bit, and we will spend some time showing that the fast Fourier transform algorithm that we have discussed in detail in the context of polynomial multiplications can actually be applied to signals in signal processing. So, let us now briefly look at how the fast Fourier transform algorithm that we have studied in the context of polynomials can be applied to discrete periodic functions. Recall that the Fourier transform of a periodic function will require an infinite number of sinusoids. So, really the Fourier transform, the Fourier spectrum will be an infinite set of points, sequence of points. However, we made life a little bit easier for ourselves when we sampled the Fourier transform at discrete locations, and we got a discrete periodic function, and the Fourier transform of that discrete periodic function will only require a finite number of points. So, as we have shown in this example, we have, let us say, this periodic function, and we have only shown one period, and this period has been sampled at some discrete points in time. And so, we can then take the discrete Fourier transform of this discrete periodic function, and we can represent the periodic function as a in its frequency spectrum. So, this is going to be the Fourier transform that we want to achieve. Recall that if we are talking about a discrete periodic function, it can be represented by a finite vector based on the value of the function at the sampled points. And so, this vector can be represented as a equal to a 0, a 1 up to a sub d minus 1. And it is not hard to see that the discrete Fourier transform of this vector is we denote that by the vector c can be written out in this manner. Each of the ck is a summation going from j equal to 0 to d minus 1 aj times e to the negative I, where I is the root of square root of negative 1 times 2 pi j k divided by d. Now, this will require a little bit of care to arrive at this form. So, we are not going to delve into the details of how we arrived at this formula, but the important thing to notice is that we are essentially using the principal dth root of unity here as well. So, we are here you notice that we have e to the minus I times 2 pi divided by d. So, that would be the principal dth root of unity. So, note once we notice this, we can rewrite the formula for C k as summation going from 0 to d minus 1 a j times omega being the principal dth root of unity raised to the power j times k. And this DFT computation can be written as a matrix times a vector. So, we can we are given the discrete periodic function as a vector A, and for an appropriately chosen matrix M, if we perform the multiplication matrix M times the vector A, we will obtain the Fourier transform of A, which is the vector C, essentially the frequency domain representation of the vector A. So, this matrix M must essentially encapsulate this equation that we have here, and when we expand it out for using the appropriate dth root of unity, we get the full form of this matrix times vector shown in this slide. And you will immediately notice that the form of this transformation matches the form of the transformation we performed in the context of polynomials. So, the exact same algorithm, the fast Fourier transform algorithm that we employed in the context of polynomials, can be applied to take a discrete periodic function, the vector representation of a discrete periodic function, and have it transformed into its frequency spectrum. So, this completes our understanding of how the fast Fourier transform algorithm that we developed in the context of or that we studied in the context of polynomials can also be applied in the context of signals, and in particular discrete periodic functions. Thank you.